Okay, in this section, this lecture, we're going to work through section 1.4 on exponential functions. Let me share my screen. All right, so as I said, we're going to work on section 1.4 on exponential functions. So basically, given you can define this function f, let's say actually any exponential. So any exponential function is of the form. So it's going to be some function f from all the real numbers to the positive numbers, and it's given by the following formula. And this is going to be for some b greater than 0, but not 1. And the reason why is that um, if b is equal to 1, then f of x is equal to 1 to the x, and that's just 1. For actually, you probably don't know this notation, but so I won't use this. And that would be for all x real numbers. So it'd be boring. So this we want b to be positive, but we also want it to be non-zero, not equal to 1. And that's just because you'd get a boring function. You just get the constant function. So f of x would always be equal to 1 for all x. So we rule that out. So this is an exponential function. B is called uh, the base. Let's say let's see. B is called the base. So it's exponential. It's an exponential function with base b. B is a positive number. It's not equal to 1. So first of all, you might wonder, okay, well, how do we evaluate this? So it turns out we actually run into some trouble when we want to evaluate this function. When x is equal to n, that is a positive integer. So n is something like 1, 2, 3, etc. It's not hard to evaluate it. So f of n is going to be equal to b to the n, and that's just b times itself n times. So they're going to be n factors, and that's exactly what we have written right here. So it's just repeated multiplication. So when you want to evaluate an f at an integer, a positive integer, you just do this repeated multiplication n times. So okay, so that's pretty straightforward, not bad. So we know how to evaluate the exponential function for positive numbers. If we have 0, then we know that b to the 0 is 1. So f of 0, it's going to be b to 0, and that's 1. So check. We can do f of n, check. And we can even do x as a negative integer. And we just set up this convention that b to the, so this is going to be f of negative n is equal to b to the n of 1 over b, and that's going to be just 1 over b times b times b. And we know how to compute fractions like this. So so far, there's no trouble with evaluating this exponential function. We can evaluate it positive integers, we can evaluate it as 0, and we can evaluate it at negative integers. And we can even do rational numbers. That's not a trouble. That's not a problem either. So if I give you x, if x is a rational number, it's going to be of this form right here. X is going to be p over q, where p and q are integers, and we can just assume that q is positive for a moment. Then we have right here is b to the x. So let me just write this on the side. So f of p over q is going to be b to the p over q. And this would just be, for example, I mean, there's a couple ways to interpret this. You can say it is the qth root of b to the p, or which is the same thing as you take the qth root of b and then take that whole thing to the pth power. Either way, you can evaluate it in either way. And again, we know how to take roots. We know how to take roots. So for example, q of b is some number x, let's say not x, let's say it's some number uh, a such that a to the q is equal to b. That's how you evaluate this qth root. It's just that it's the qth root of b is just that number such that when you raise, it's that number a. So let me just rewrite this. It's that number a such that when you raise a to the qth power, you get the thing under the square root. So for example, square root of 4 is 2 because when you take 2 and raise it to the second power, you get 4. Or the square root of 9 is equal to 3 because when you take 3 and square it, you get 9. That's how roots work. So again, there's no problem. We can evaluate exponential functions even at rational numbers. But here's the problem. What about if our x is irrational? How do we deal with that? So for example, how do we deal with 2 raised to the square root of 3 or 5 raised to the pi? So square root of 3, pi, these are irrational numbers. So you can't, it's not a fraction. So if I want to evaluate our exponential at say root of 3, so in other words, like what is this? What is that equal to? How do I make sense of that? Well, for one, square root of 3 is irrational. So that means it's not an integer. So that means I can't do some sort of repeated multiplication like I did up here, right? But it's also not a fraction like this right here. So I can't do some sort of root, I can't do some sort of calculation like this. I mean, what does it mean to multiply? What does it mean to multiply a number by itself square root of 3 times? It doesn't make sense. And interestingly, actually, the only way to answer this question really is you need calculus. So kind of cheating here, and we're going to cheat here because you can't technically define the exponential function without calculus, but we're going to just kind of sweep the details under the rug. So that's kind of unusual. Like you actually need a whole branch of mathematics to define a function. And this is actually pretty common. Like you need to develop a lot of theory in order to make sense of certain things. So we're all familiar with like what an exponential function is, or roughly familiar with it. But it turns out that you can't define it without first developing the theory of calculus. So here's a graph of, oops, I didn't mean to do that. Here's a graph of 2 raised to the x for x rational. So oops, I don't know what's going on here. You can see that there's gaps, there's these holes, because we can't evaluate 2 to the x at a irrational number. So we have these gaps. But it turns out that the irrational it turns out that irrational, or I should say actually rational numbers are so-called dense in the set of real numbers. And that just means that like even though they're really spread out, they're like they really fill out the space of real numbers. There's a lot of rational numbers. And what that means, like this word dense has actually has a very technical math definition. And basically it means that for at least real numbers, density means that if I give you any two numbers in um on the real line, you can find a rational number between them. So given any real numbers, you can find a rational between them. So and that's basically what it means to be dense. Um, it gets more technical when you so like our real numbers, we have a inequality on them. We have a relation on them of less than or equal to. So there's some spaces where you don't have less than or equal to, but you can still talk about dense subsets. So the rationals are dense. And what that means is that, hence what we can say then is that every number can be, and then we can be approximated. Put this in quotation marks too. Approximated by rational numbers. And that's what we're doing over here, actually. We're approximating 2 raised to the square root of third power by rational numbers. So what that means is that, and this is actually exactly what your calculator does. If you type in square root of 3 and you want, if you type in square root of 3 to your calculator, you're gonna get some decimal. I mean, I can even pull it up actually. Let's see. So if you type in square root of 3 and hit Wolfram alpha, you're going to get roughly 1.723, etc. This is an irrational number, meaning it has infinite number of decimals. So, but you can see we chop it off here. So this decimal approximation isn't the actual number square root of 3. It's a rational approximation. This number right here is a rational number. It's a rational number and it's approximating it. And you can add more decimals to this approximation to get a better approximation. And so what this means is that every number can be approximated by rational numbers, and every number is, in a sense, a limit of rational numbers. So let me say that too. Every number, and we're going to talk about limits a lot in this course. That's like the whole foundation of calculus, this notion of a limit. So every number is a limit of rational numbers. But this is good for us. Why? Why is this good? So here's the notation we use. So so given some real number R, there exists a sequence. So like Q1, Q2, Q3, all the way off to infinity. Let me make this a little neater. So it's good to talk about limits because they're going to come up a lot. So there exists a sequence Q1, Q2, Q3, and this is of rational numbers. So these are all rational numbers, such that R is equal to the limit, and I'm going to put this all in quotation marks because we didn't talk about limits. I haven't defined everything properly, but hopefully the idea is clear. It's like the intuitive idea. So R is going to be the limit of these rational numbers. So this sequence goes off to infinity. Like you have Q1, Q2, Q3, Q4, all the way up. And these numbers, these rational numbers, they approximate this number R. They get closer and closer and closer. And because of that, we can define, so now what this means is that if R is irrational, then we can define f of R to be the limit. Let me see. Run out of room here. So let me say then f of R, then f of R is going to be the limit as n goes to infinity of f of Qn, which is the limit as n goes to infinity of b to the Qn. Now, this might look kind of confusing, and that's okay because this is kind of jumping ahead of it. But this is a good formula. Why is this good? Because now, before we knew this fact about real numbers, meaning that the fact being that every real number, especially in particular every rational, irrational number, can be approximated by rationals. That allows us to define f of R. That is, it allows us to define what it means to take the exponential function and apply it at this irrational. Basically, you do this computation right here. So Qn is an irrational number, and so we know what it means to take b to the Qn, right? We did that up here. We know how to evaluate our exponential function at some rational number. And so because we can do that, and then we can take this limit, whatever that is, it's like basically it's like you have this sequence of numbers and they're approaching some number. And the number that they approach, it just is the limit, the number that they get closer to. And so I can take b to the q1. So I basically what happens is I get b to the q1, b to the q2, b to the q3, etc. So given this sequence of irrationals, or sorry, of rational numbers, I can form this sequence here, and this is going to approach some number. Whatever that number is, call it f of r. And so now you can extend the definition of the exponential function to the irrational numbers. So this is kind of like a scaffolding process. Let me just summarize what we've done. So we want to define this exponential function and we want x to be able to be any real number. Well, we start with x being a positive integer, and this is how, right here, how we define that for x positive integer. And then we define x0 to be 1. And then we can define x to be a negative integer as follows, using this formula right here. And then we can extend that definition to x being some rational number. So it's like we're doing this, we're defining the exponential function in stages. And then the final stage is, how do we evaluate the exponential function when x is irrational? And this is how you do it. But you use this fact that the rational numbers are dense in the set of real numbers. So that means every real number can be approximated by rational numbers. And what that means in more technical terms is that if I give you any real number, you can find a sequence of rational numbers such that that number you started with is some sort of quote unquote limit of these rational numbers. And so if r is irrational, which is what we're trying to do, we're trying to define f of r for some irrational number, we can define it as this limit right here. So I can form this sequence right here. So given this sequence right here, I can form this sequence right here. And this sequence right here is gonna approach some number, and you just call that number f of r. So now we've extended the definition of exponential function to irrational numbers. And this whole they're doing this for a specific example right here. So let's look at this concrete example here. So they have f of 2 to the x. You have this irrational number square root of 3. And you can see that this function is an increasing function, right? This is increasing. The exponential function is increasing. So here's a decimal approximation. So let's actually call it a rational approximation of square root of 3. So we don't know what 2 raised to the square root of 3 power is, but whatever it is, it's got to be between this number and this number, both of which are rational. We can compute this number and this number. These are rational numbers, and we know what it means to evaluate the exponential function at rational numbers. And we can just keep repeating this process. Look at, so we can add more decimals. So we had 1.7, and I have 1.73. We had 1.8, but actually you can do better and say it's 1.74. And look at, you have these numbers, these numbers on the outside, they're getting closer to each other. So the square root of 3 is like stuck between these numbers, these rational numbers, which are getting closer and closer to it. And square root of 3 is just the limit of these rational numbers. And then you can form over here. So if I have that square root of 3 is bound between this and this, then this 2 raised to the square root of 3 is bound between this number and this number. Square root of 3 is bound between this number and this number. Then 2 raised to the square root of 3, 2 raised to the square root of 3 is bound between this number and this number. And all these numbers, this number, this number, this number, and this number, this number right here, this number here, this number here, and this number here. These are all rational numbers. It's 2 raised to some rational number, and I can compute that. And so you can see that you have these dots here, meaning like basically you're repeating this process of approximating square root of 3 indefinitely many times, an infinite number of times in a sense. So it says can be shown that there's exactly one number that is greater than all these numbers and less than all these numbers. And then you just simply define 2 to the square root of 3 to be just that number that's greater than all these and less than all of these. It's going to be this limit of this sequence here. And so I mean that's exactly um what I said earlier about what I did earlier over here when I wrote down all of this. This is basically the same process here. And so you can do it for, as I said, you can define 2 to the x where x is any irrational, kind of going through this similar process of taking your irrational number, fitting it between taking your irrational number and fitting it between 2 rational numbers and like getting better and better approximations of it, and then taking a sort of limit. All right, so that's how you define that. And this is all these ideas are like at the foundation of calculus. So you cannot define this function without using ideas from calculus and talking about limits. And again, all of this should be in like quotation marks because technically haven't defined what does it mean to take a limit, but hopefully it's somewhat like intuitively clear what a limit is. It's like you have this sequence of numbers, and they're approaching some number. So let me actually write an example. Here's a really simple example of a limit. So the limit of 1 as n goes to infinity of 1 over n is, what do you think it is? Well, I'll give you a second. I'll let you pause and try to think about it. What that might be. And if you paused and you thought about it, and you thought that the answer is 0, then you got the right answer. And why is that? Well, let's look at this sequence, 1 over n. So you have n is equal to 1, n is equal to 2, n is equal to 3, etc. Well, when n is equal to 1, you have 1. When n is equal to 2, you have 1 over 2. Let me actually add some more. N is equal to 4, and then dots. When n is equal to 3, you have 1 over 3. When n is equal to 4, you have 1 over 4. And you can see the denominators are getting bigger and bigger. So you have 1 over a big number. And these numbers are getting smaller. So these numbers in the sequence are getting smaller and smaller and smaller. And they're in fact approaching 0. And that's all that this symbol means. It's just meant to express the fact that when you write out this sequence here, 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, etc. This sequence is tending towards, it's approaching, it's converging to 0. These are all different ways of expressing the same thing. So, and again, we'll make this more precise, the notion of a limit later on. All right, so here's some examples of the graphs of this function. So basically you have these 2 cases. You have that b is between 0 and 1. And then you have b is greater than 1. So you're really only going to have 2 shapes. This is way more complicated than it needs to be. So you have 2 shapes. When you have b between 0 and 1, well, first of all, okay. So our function f of x is equal to b of x. And you have 2 cases. You have b is between 0 and 1. And the graph of f in this case looks something like this. And it goes up like that, and it goes through 0, 1. Okay, so that's the one case. Here they don't. Actually, they write it here. So I won't even write the other one. So when b is between 0 and 1, your graph looks like this. This is the b is equal to 1 case. It's just a horizontal line, so don't even care about that case. That's never going to come up. And then you have the case where b is greater than 1, and it looks like this. So just remember those. Yeah, so these, just remember these two right here, this one and this one. These are the most important ones. So now that we know how to take evaluate exponential at any real number, we can establish some laws of exponents. So we have that b to the x plus y is equal to b to the x times b to the y, and then you have b to the x minus 1 is this fraction. And then this says when you have a power and raise it to the power, you just multiply the powers. And then the power distributes over a and b like so. All right, so let's see. We have, sorry. Oh, I don't think there's a whole lot more to do. Okay, so let's go through this example. Um, so we have this function negative 3 minus 2 to the x. So we know what 2 to the x looks like. I think they're going to graph it right here, yes. And now when you negate it, remember when you negate the function, when the negative goes on the outside as opposed to negating the x up here, that means you reflect over the x-axis, and that's what they did here. And then finally, when you have this 3, when you add the 3, you're going to shift the graph up. The best to figure out where exactly to shift up, just remember that this line right here, the x-axis, is a horizontal asymptote. And I'm gonna recall the definition of horizontal asymptote later. But basically, what that means is that when you want to graph some vertical translation, like this function here, you need to not only shift the graph up, but you need to shift up its horizontal asymptote, and that's what they did here. So the horizontal asymptote is y is equal to 0, and that's going to shift up 3 units to get y is equal to 3, and then the exponential is going to approach that line. It's going to get arbitrarily close to it, but not ever go through it. So that's how you graph that, and I guess yeah. So the domain is still the same. It's the same as the exponential function. The range is different. Remember, if I give you function, let's say actually, so if I have f of x is equal to b to the x, the range or the image is going to be all the positive numbers, and that's what you can see. You can see that in this graph right here. It's going to get arbitrarily close to the x-axis, but it's never going to touch it. So that's why you don't include 0 in the image. It's excluded. It never goes to the x-axis, but you can get arbitrarily close to 0. So the image of the function does hit every positive number. And when you do that, you have to shift the x-axis up and reflect it. And so what that means in this case is that the range is going to be -3 negative infinity up to 3. So the range here, the range for this function is just going to be negative infinity to 0, but then you got to like shift up this is the image, I should say. This is the image of this function right here. But then you have to shift everything up 3 units. So that's why the image goes it goes from being negative infinity to 0 to negative infinity to 3. All right, so we'll skip that. That's not really that important. And then so the next thing we want to look at is this particular number e. We're gonna mostly look at functions of base e. So e is called well, let's say it's approximately 2 point, I don't even remember, I have to look it up actually. It's I don't know. Oh yeah, so it's approximately 2.71. It's called Euler's constant, and it's irrational. It's an irrational number. We're typically going to look at our exponential function as to this base. So it's going to be f of x is equal to e to the x. So E is a constant. It's this constant, approximately 2.71. And this number, Euler's constant, actually has a lot of unusual properties. Not unusual, but surprising and interesting properties that makes it easy to or to work with. So there's a lot of ways to define the exponential function, and it like kind of comes up in a lot of different ways. So let me see. Well, okay, so here's some let me actually pull up one note and then write some properties down that it has. Oops. So properties of E. So the first two properties that are really relevant for us are the following. So I haven't talked about derivatives yet, but maybe you've heard of this concept before and maybe even know about it a little bit. It turns out E, when you take the derivative of this exponential function, you just get E to the X. So it has this very nice property that it's its own derivative. So in other words, you can say that e to the x is a fixed point for differentiation operator. So to compute the derivative of e to the x, very easy. So here's one interesting property. Another interesting property, and it has to do with integration. So it is the following, that if you integrate from 1 to e of 1 over x dx, you get 1. So it's this number such that when you do this integral, again, don't know, I haven't talked about integrals yet, so not expecting you to understand what this means, but just like a preview. What this says is that the integral basically gives you the area, and so if you plot 1 over x from e to the x, it looks something like this. And so you have 1, and then you have e, and then the integral gives you the area, say, from here to here. And it says that this area, this number e, has this property that when you compute this area, it's just 1. So that's kind of interesting. E also appears as a limit. So E, and this is one way of defining e to the x. Or sorry, E. It's the limit as x goes to, actually, let's say n goes to infinity of 1 plus 1 over n to the n. So E is this number that's the limit of this kind of crazy looking sequence. If you go to Calc 2, you'll find that E is also this sum right here. This is an infinite sum. This, if you're not familiar with this notation, that's okay. We will learn about it later. But it's this infinite sum here, and I can just expand it out a bit. So it's like 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, all the way to infinity. And k factorial is just, you take 1 times 2 times 3 all the way up to k. So you take the product of the numbers 1 up to k. So like let's say 3 factorial would be 1 times 2 times 3, which is 6. And then 4 factorial would be 1 times 2 times 3 times 4, which is, I guess, 24, and etc. You can compute the rest of them. So a lot of different ways e to the x appears. And then another one that I like, now we're not going to talk about complex variables very much in this course, but I think most of us know that I is this imaginary number or unit. It's the square root of -1. And this e to the x has this unusual property that when you take e to the I times pi, you actually get -1. So this kind of illustrates how unusual number e is and how unusual these complex numbers can be. Because we know that when you raise a number to any positive number or any number, you're going to get a positive number. But somehow when you raise e to this imaginary number times pi, you get a negative number, which is kind of bizarre. So this has a lot of unusual properties. It's a very nice number. and it kind of simplifies calculations. All right, anyways, so um yeah, I don't really want to talk about this because there's no point going over that. Um, let's see. I guess we can go over this example 2 or 5 quickly. So we have this function here. We want to graph it. So we have graph e to the x, and it just basically looks like any other exponential function. You can't really tell the difference between the exponential functions. It's kind of hard. Now in the function here, we have e to the negative x, so we have to negate the x, like we do here, and that has the effect of reflecting over the y-axis. And then you have 1/2. The 1/2 is on the outside of the function, so that means you're shrinking all the y coordinates, so that's why it goes, this point shrinks down to here, or it like kind of shifts down. This is not a translation, that's like a shrinking. So this point shrinks down to this point here, like we do here, and then we're subtracting 1, which means we're shifting things down vertically, and that means we have to shift the asymptote right here to 1/2. So this line right here is on, oh, they already write it. It's -1 right there. So that's the graph. And you can see that, first of all, the domain is all of R still. The domain doesn't change, but the range changes right here. All right, so that was all for this section. This is a pretty short section.